the supply channels and feeder channels. Every irrigation tank has a catchment area draining into the tank. It could be as small as 100 hectares or as big as 1000 hectares catchment area. In the catchment there will be small gullies, tributaries to the main stream leading into the tank. When a rainfall occurs, these gullies, tributaries as well as the main stream will naturally gravitate into the tank. There is no need to make channels within the stream bed. In several cases, it is noticed that channels are made within the stream bed with the idea that the runoff water may go without interception anywhere in a fast manner to the tank. Now this is a sort of an illusion. The rainwater collected in the stream will naturally find its way downstream and it has no other way to go anywhere else. If supposing the bed is silted already, then even in a silted bed, the runoff water which collects there will have to flow down. It cannot be stored in the stream, or it is not being diverted from the stream to somewhere else through any structure. So the natural slope of the stream will make the water flow into the tank. But some people say it is going slowly. We want it to go fast. But here there is a sort of a lack of understanding. If a certain quantity of water gets collected into the stream, whether the velocity of flow is less or more, it makes no difference with regard to the water going into the tank. The runoff water, if it travels at a low velocity, then it will take more amount of time to draw the flow entering into the stream. If supposing it goes with a higher velocity, then the time taken for the water to travel to the tank would get reduced, but the quantity is the same. Whatever runoff quantity that collects into the stream only will go into the tank. Whether it goes slowly or it goes fast, the amount of runoff collected in the tank will not be varying much. Here there is one contradiction. That is, all the watershed development works we are doing, they are aimed at making the running water walk. According to our slogan, we have to see that the running water walks, the walking water stops. The idea is that we should increase the deep percolation, infiltration into the soil and recharges the water table. Now here, if you make channels within the stream course, we are making the walking water run, contradicting the very principles of watershed management and contradicting the crores of rupees we are spending to achieve that objective of a running water walk. We are spending money here to make the walking water run. Is it not a contradiction? So we should not attempt this type of contradictions, contradicting the watershed principles in trying to make it run faster. There is one point here. When the water is moving with a low velocity, certainly there will be more contact time with the earth and therefore there would be greater deep percolation. So the water reaching into the tank will slightly get reduced depending upon the increased time for deep percolation within the stream bed. These are all minor issues and then they go with the watershed principles, and therefore there is no need to have a channel excavated in the stream bed. Now let us see if we spend crores of money, in fact hundreds of crores of rupees were spent for such channels, let us see whether they are sustainable. This is one important issue. Now supposing a stream is having a maximum flood of about 800 cusecs, it's about 500 hectares of catchment area, and it's having about 600 to 800 cusecs flow during the maximum floods. The channel that will be made, usually in the bed, will have a carrying capacity of about 30 to 40 cusecs. This is very much less when compared to the maximum flood discharge. So now it is clear that there is no need for a feeder channel, what they term it as feeder channel, that is a channel excavated within the stream bed to augment the supplies of the tank. There is no need for such thing because it neither increases the flows into the tank significantly and because it violates the principles of watershed management. With all that, even if this is sustainable, this is something which the farmers can feel contented, but it is not sustainable. This again gets silted up and it will not be in that shape of excavated channel, and it's very soon it will be going out of shape. Now let us discuss about the supply channels to the irrigation tanks. This is totally different from the stream bed channels or feeder channels which we have discussed just now. This is supplying additional water from a neighboring sub-basin to the irrigation tank. We already said each irrigation tank has got a catchment area. So any rainfall runoff occurring within the catchment area is bound to reach the tank. In addition to such runoff within the catchment, there would be a need for taking more water from the neighboring catchment, neighboring sub-catchment. If in case more water is needed for the tank, the runoff occurring from the neighboring sub-catchment or sub-basin can be diverted to this tank. Such diversion channels are termed as supply channels. Supposing there is a fairly big stream flowing close to the catchment area of the tank and draining into some other sub-basin, we can have a diversion structure called an anicut, or there could be, even without a diversion structure also, a channel can be excavated and this will run along the contour. There won't be steep slopes in this, just the required slope for the canal to flow, and that will be running on contour, and it would supply to one tank and also perhaps to number of tanks. There are such supply channels already existing in many of the tank systems. We call such a thing as system tanks, that is a diversion canal from a stream of importance, taking off from a headworks like an anicut, runs in contour and feeds a single tank or a number of tanks. Usually there would be 6 or 8 tanks which get supplied from such a neighboring important stream, and this crosses the drainage courses of various tanks and it will empty into the last tank. So these are all called supply channels, or to put it correctly, diversion channels. And these channels are mostly silted up, or some of them are in a bad shape, breaches also, and some of the structures, that is the drainage structures, are not functioning properly and they need rehabilitation. So the rehabilitation of such supply channels can be taken up on a sustainable basis. In many cases, we notice that only desilting being done for such channels. Desilting alone is not a sustainable operation. Again it gets silted up, and desilting may have to be done at very regular intervals, otherwise they get disuse. In addition to desilting, there are three important aspects, three technical aspects which have got to be looked into in order to make the supply channels sustainable. Now these supply channels, as we know, they take off from an anechoic structure usually. Upstream of the anechoic structure, a repulsion groin has got to be provided. This is nothing but a rubble stone structure of about 10 to 30 meters long and having a particular angle in order to repel the silt coming in the stream, in order that this silt may not enter the diversion canal. The groin helps in repelling the silt from entering into the diversion canal. So this has got to be designed, and the irrigation engineers know how to design this, and this is a very cost-effective structure, could be as cheap as about 4,000 to 5,000 rupees. And this structure would be useful in preventing silt flow or flow of sand into the diversion canal. That is the first technical intervention. The second thing is, there will be runoff entering into the diversion channel all along its length. Because it runs in contour, one side of the canal is having a sloping ground going into higher levels. Other side of the canal will be sloping down. So the side which is having sloping up, when rain occurs at that place, there will be a runoff, and this runoff collects into the diversion channel. And when that runoff collects into the diversion channel, the flow in the channel gets increased, and such flows will cause breaches wherever an embankment or partial embankment reaches. The diversion canal would get breached. As long as it is in cutting, no problem. But there will be some partial embankments or full embankments where they cross natural drains, and in such cases they are vulnerable, and any increase in flow in the channel would cause a breach. So the runoff entering the channel from the sloping up areas will have to be safely discharged from the diversion canal, and this can be done by suitably designed outlets. These outlets, if they are already existing, they have to be maintained. If they are not existing, they have to be constructed. In addition to these outlets, there would be a need for having a catch drain all along the diversion canal wherever there are steep slopes on the upper side. The purpose of this small catch drain of about half a meter by half a meter is to prevent the soil runoff or silt from entering into the diversion canal, and it intercepts the silt as well as a portion of the runoff. The other intervention is that all the cross masonry structures like super passages or aqueducts, they have to be maintained properly. Most of them are in a bad shape. Unless these three activities are taken care of, the diversion canal will not be sustainable. Just desilting will not help. It will again be silted later on, and it will not be sustainable. Though it may cost a little more to do all these things, it is preferable to do it on a sustainable basis, following the technical guidelines issued by the Chief Engineer, Minor Irrigation.